I'm now going to talk about sparse linear regression. This is our first exposure to, how sparsity can be used to get a different solution from if you don't impose sparsity. So let me remind you first about the standard linear regression problem in vector form. So standard linear regression, what does it look like? In the context of, the explicit feature vectors, I should remind you that the loss function after I have demeaned the data and the target looks like I have the feature matrix times the regressor I'm trying to find minus the targets, the L2 norm square of that. So reminder, if there are n examples, this is n cross 1. This is n cross the dimension of the feature vectors. So this is also d cross 1. And then you have a regularization term that we had taken to be the L2 norm squared. And I'm going to be explicit here, L2 norm squared of W. So now if we want W to be sparse, then one very standard approach to do it is to take an alternative cost function, which is, still I want my predictions phi w's to be close to my targets y's, right? I still want that, but I'll impose sparsity by taking an L1 norm constraint, right? So basically, what does sparsity mean? Sparsity means we want W to have a small number of non-zero entries, right? So actually what that means that we want the L0 norm of W, L0 norm, to be small, right? The L0 norm is just a number of non-zero entries, but the L0 norm is not necessarily that tractable for if you want to find a global optimum, and it turns out the L1 norm is a good proxy. So L1 norm is a good proxy. Why is it a good proxy? Because this cost function that we have, this is actually convex, which means I can find a global minimum easily by a number of techniques. So before we go on and say how we are going to solve this problem, let's get some intuition as to what's the difference between the L1 norm and the L2 norm. Okay, so remember what I'm trying to do with the L2 regularization. Let's look at what the problem is. I'm trying to fit phi W to Y, and I want the norm square of W to be small. So let me try to get intuition not by the original problem, but by saying, okay, what if I think about minimizing the L2 norm of W such that I exactly meet my targets, that phi W equals Y. It's just easier to give intuition for this related problem. So, and I'm going to try to give this intuition in a two-dimensional setting. So what are we doing? So this phi W equals Y is a line. Let me say that it's a line like this, right? So this is my phi W equals Y line in 2 dimensions. And what is W squared? This is basically a circle, right? So this is W1. I don't know. I'm going to call it W1, W2. These are the 2 components. And I want basically to, let me change pen color. I want to grow a circle until it hits the line. I want the smallest radius circle such that I hit this line, right? So in this picture, this will be my W opt, which is the smallest L2 norm squared such that I satisfy this constraint, right? Okay. Let me now do the same thing with L1 norm. So with the L1 regularization, but I'm now going to put it the other way, I am going to minimize the L1 norm of W, which is of course the sum of the magnitudes of the two components, such that phi of W equals Y, right, in this formulation. So what does the L1 norm being smaller than something mean? Let me just draw the 2D picture again. For example, these two guys, if I take a typical line, there's a W1, W2 here. If I take suppose this intercept is 1, then this box is L1 norm of W being precisely equal to 1. That's what this box is, because this is W1. Let me change pen color so you can see what I'm doing. This line is both of them are positive, and I have W1 plus W2 equals 1. In this one, W1 is negative, so basically I have minus W1 plus W2 equals 1, etc. Right? So essentially this box, now I can draw the whole box, is magnitude of W1 plus magnitude of W2 equals 1. So I basically have to grow this sort of side tilted box until it touches that line. That's basically the picture that I now have. So let me redraw my some picture with this line, and then see how I would grow a box to hit it, right? So let me redraw the picture in 2D of the coefficients W1 and W2, and draw a line, some arbitrary line, phi W equals Y. This is the targets that I'm trying to hit exactly in this case, right? And changing pen color, I'm going to start growing these. I'm not necessarily getting the slopes exactly right. The slopes should all be 45 degrees. So I keep growing these guys until it hits the line. So maybe it hits it like this, I don't know. Maybe not. Let me see. So I keep sort of growing this. These are just sort of parallel 45 degree lines, and this one I've chosen so it's not exactly 45 degrees. So it's important for me to draw this kind of precisely to make my point. So unless this phi W equals Y line is 45 degrees in this particular case, I will hit it in a corner. So in this corner, I remember this is W1, this is W2. In this corner, W2 is 0. So with if I can think of the lines as having arbitrary slopes, that the slopes follow some sort of uniform distribution over the set of possible slopes, then the probability of the line being exactly aligned by the side at 45 degrees is essentially 0. So for pretty much every line, you will, as you grow these slanted boxes, you will hit the line at a corner point, and where one of the coefficients will be 0, right? You can see that the same is true for some line like this. It'll also hit you at a corner of the thing. So unlike the L2 norm regularization, where the tangent to a circle will typically have both coefficients non-zero, with the L1 norm regularization, you are basically with very with probability 1 in this scenario. If I take the probability over, if I take some uniform distribution of slopes, you will hit it at a point when one of the coefficients is 0. So basically, L1 boxes are pointy, which means sort of the intersections with the kind of constraints we have, intersections are likely to be L0 small in L0 norm. So that's basically why the L1 constraint works and is tractable because it's a convex function. It's not differentiable everywhere, but it's convex. Okay, so now that we have developed some intuition as to why L1 constraints make sense for promoting sparsity, let's write down the problem that we are after. So we have a loss function, which is I'm basically doing this linear estimates based on the feature vectors and trying to approximate the target using an L2 norm squared, and I have an L1 regularization on the regressor, lambda times the L1 norm of W. This is called a lasso problem. There are lots of canned programs that you can use. You can use canned programs generically for convex optimization, but in particular for lasso, there are of course even better solutions because it's a very simple problem, quadratic plus L1. What we are going to do is actually, since you can use canned programs, my only objective here is to give you some intuition as to what the solution looks like, and that's easiest to give by actually a particular just going through a particular procedure for doing this optimization, doing this minimization, and that's cyclic coordinate minimization, right? So basically, I'm going to optimize this coordinate by coordinate and keep cycling through until I'm done. When am I done? I'm done when the so-called KKT conditions for this convex problem are satisfied. I do not have time to go through the general theory of convex optimization, so I'm actually just going to talk about this particular procedure in a very intuitive way, with the purpose only being to reveal the structure of the solution. Okay, so before I go on, let me just twiddle with the cost function a little bit. So basically remember that this quadratic term is the sum of the squared errors over n examples, right? And we are basically balancing how much weight to give to that and how much weight via lambda to give to the sparsity term W1. Remember that this term does not scale with the number of examples. So in order to make make sure that I can throw more examples at the problem without needing to change lambda too much, I should really normalize that first term. So I'm going to do that. So 1 over n phi w minus y L2 norm squared plus lambda L1 norm. Hopefully with this change, I won't have to keep adapting lambda a huge amount as I change the number of examples. The other thing I'll do is just for prettiness, I'm just going to put another factor of 2 here below, because when I take derivatives of quadratic terms, there's a factor, there's a 2 that comes in the numerator. I just want to cancel it out so that things look pretty, okay? And I'm still going to call it L of W. I'm not going to change notation for that, but this is the cost function I'm going to optimize via this cyclic coordinate minimization. So let me introduce some notation. Let me look at what the impact of the jth coordinate is going to be. So let me take a quick example. So I have a phi, which is, let's just say, two examples. So phi 1 and phi 2, and then basically I have phi 1 1, phi 1 2, phi 1 3. So I have basically just three features, right? Three-dimensional. Each feature vector has three dimensions, and I have this guy, phi 2 1, phi 2 2, phi 2 3. So this is my phi matrix, and I'm going to multiply it by a W, which has the same number of dimensions as the number of features. So W looks like this, right? And suppose I want to optimize over this W2, keeping W1 and W3 fixed, right? So basically, remember, W2 will only be multiplying these guys, right? The second feature of all the examples, right? So basically, I can say, let me call phi of phi of 2 as the basically the second column, right? Phi 2 is the second column of this guy. Remember, it's not the second example; it's a second column, meaning basically the second feature of all examples, right? So column 2 of phi matrix, which is second feature of all examples, right? So basically this is an n cross 1 matrix. And let me say phi of minus 2 is phi without the second column, right? So basically it's the parts that, it's the features that will be corresponding to the frozen weights, right? So in our case, that is, phi 1 1, phi 2 1, phi 1 3, phi 2 3. So what's happened? I have it's n cross d minus 1. I've just eliminated exactly one of the columns corresponding to a particular feature. And let me do the same thing for the W as well. By the way, remember that we always use subscripts to denote the examples typically, but I don't really need to be so careful when I'm talking about the and that's for the phi matrix, right? That's why we reserve the subscript for the examples of phi 1, phi 2, etc. W, I don't need to be quite so careful. Let me just and I prefer subscript to superscript. So let me say that W of 2, that's the same as W2. I'm gonna just be, it's less less cumbersome. So that's the one that I'm gonna adapt, and then W of minus 2 is W without W2, right? Which is just, in our case, just W1, W3, right? So I'm setting this up so that now what you know is that this bunch of predictions that you have phi W can now be easily written as the part that does not depend on the second coordinate that you're trying to optimize over, and the part that does depend on this second coordinate that you're trying to optimize over. And actually, I'm actually going to denote this not by phi of, I'm just going to do this phi of minus 2, meaning everything except the second column, right? So now if I look at the error, which is the targets minus the predictions, that is equal to basically the target minus phi of minus 2 w minus 2 minus phi of 2 w2. And if we look at what this term is, this is the error in the prediction based on everything except the second feature, right? Let me call this r of minus 2, which is y minus phi of minus 2 w minus 2. So this is a residual error when we use using all features except the second one. So remember now that my cost function was the quadratic term of the error, which I can now write as E transpose E, where E is that guy, plus lambda times the L1 norm of W. Now, if I've frozen everything except the second coefficient, what's the part that depends? So this was L of W. What's the part that depends only on the second guy? Well, this one does depend on the second guy, but I can write it as, remember the error is, what is it? R minus 2 minus the second feature across all examples times W2, that transpose itself, right? R minus 2 minus phi 2 W2. And then if I've frozen all the other terms, then only the magnitude of W2 in this L1 norm term contributes to this. And now I can, so this is a 1D optimization over W2. It becomes really, really simple. And remember that we had also done this nice sort of normalization 1 over 2n there, so I'm going to put that back in there and back in there as well. Okay? So now let me just, so we tried to get these concepts down using that example, but let me just restate sort of generally what the notation is, right? So basically I have phi of j is the jth column of phi, so basically corresponding to jth feature, the jth feature. Let me just erase this jth feature. Wj is the coefficient, jth regressor coefficient, and then phi of minus j is phi without jth column, and w of minus j is w without jth entry. And then r of minus j is the prediction that you have of, this is the targets over all the examples of what you do without the jth feature, right? So that's what we have, and so this is completely general now. And the cost function that we want to optimize over wj now is, keeping everything else frozen, is 1 over 2n, that's that normalization. This is just the error itself that I'm writing as the residual without the jth term minus what you can do with the jth term. I'm running out of space here, times r minus by times itself, basically the L2 norm I'm talking about, plus lambda times the magnitude of the jth coefficient. And this is what I want to do a 1D optimization over. So let me consider a simplified version of this problem to avoid messy notation and then come back to it. So let me consider the following. Let's say there's again the half, I like keeping that around to make things look nice. Half of some constant minus some w that I want to optimize over plus lambda times the magnitude of w, and let's call this a function of w that I want to minimize. This is actually a convex function. It has a global minimum. Let me take the derivative of df by dw. It's of course a minus w squared is the same as w minus a squared. So it's w minus a, the derivative with respect to w, plus what is this guy? Well, if w is positive, this guy is lambda times w. If w is negative, the magnitude is lambda times minus w. So the this output is lambda times the sine of w. This is a sine function which looks like this, plus 1 minus 1. I don't really need to talk about what happens for w equals 0. So we leave the sine function undefined for w equals 0. W equals 0 will be an important point, but we'll come to it in a minute. So let's see. So it is defined. The sine function is defined for w bigger than 0 or w less than 0. So let's see. Suppose the derivative is 0 for w bigger than 0. So suppose df by dw is 0 for w bigger than 0. So what are we saying? W minus a plus lambda times sine of w, which is plus 1, is equal to 0. So we are saying that w is a minus lambda. So remember, I'm trying to minimize a minus w squared. So if I didn't have any other term, the answer would be w equals a. But here I am actually reducing by lambda. So I'm shrinking w in some way. Similarly, let's assume df by dw equals 0 for w less than 0. In this case, I have w minus a plus lambda times sine of w now is minus 1. So this is equal to 0. So w is going to be equal to a plus lambda. So and remember that it is w in this case by assumption is less than 0. So let me go back to these two conditions and say, okay, I had assumed that w is bigger than 0 in the first case. So this happens only when a minus lambda is positive. So this happens when a is bigger than lambda. In the second case, I'd assume that w is less than 0. So this happens when a is less than minus lambda, right? So what happens in the middle when a is between plus lambda and minus lambda? So now let's suppose that a is between minus lambda and plus lambda. Let's assume that, and let's compute df by dw. Well, for w bigger than 0, it is w minus a plus lambda, just like we have computed, and this is of course positive. Why? Because a is less than lambda, so minus a plus lambda is positive, and w is positive, right? So this is positive for w bigger than 0, and it is df by w is w minus a minus lambda for w less than 0, and this is going to be less than 0. Let me just clarify again why. Here I have that lambda minus a is bigger than or equal to 0. That's why I have this. And here I have that a plus lambda is bigger than or equal to 0. So and w is less than 0. So w minus something positive is less than 0. So I have this picture. So what does this mean? That my derivative is positive when w is bigger than 0, so it's increasing for w bigger than 0, and it is decreasing. The derivative is negative for w less than 0. I apologize. I had made a mistake here. This was, of course, w less than 0. So what does that mean? That basically I have w equals 0 is the minimizing argument when a is between minus lambda and lambda. So what's the final result we get from all these things? Let me just draw what the optimal solution is for w as a function of a and lambda. So when a is bigger than lambda, w is a minus lambda. That's what this was showing. So that's a 45-degree line, but it starts at lambda. When a is less than minus lambda, it is this guy, another 45-degree line at minus lambda, and in the middle it is 0. So this is my my answer for w, and I'm going to call this s sub lambda of a, and this is a soft threshold operation, right? Basically, I'm thresholding at plus minus lambda, but I'm not saying plus 1 or minus 1 after the threshold. I'm just letting it through after subtracting the value of the threshold, right? So just to summarize, w opt in that scenario is s lambda of a, which is a minus lambda for a bigger than lambda, 0 for minus lambda less than or equal to a less than or equal to lambda, and a plus lambda for a less than minus lambda. Okay, so this is my soft threshold operation. It's a very useful thing to have under our belt. It's also called shrinkage. So let me write it again. Soft threshold or shrinkage operation. Shrinkage, why I'm shrinking by lambda, right? Okay, so let's go back now to our cyclic minimization problem. So back to cyclic minimization over each coordinate, and just a reminder that the cost function in terms of the jth coefficient was, look at the residual error when you use all the other coefficients, residual error in the target variable, and then now try to reduce it using the jth feature, right? So I have this transpose itself, r of minus j is the residual error, minus phi j wj, jth column of the feature matrix, and then plus lambda magnitude of wj. Looks very similar to what we just did, the simple problem we just did. It's not exactly identical, but when we differentiate, we'll get something the same. And of course, let me remind you that I am actually putting this convenience of normalization in, so that my lambda doesn't have to change as I change the number of examples, or change too much as I change the number of examples. Okay, so let's take the derivative with respect to wj, which will exist for wj not equal to 0, because the magnitude of wj becomes plus or minus w, and this is straightforward. Now I'm differentiating the quadratic with respect to w. I get something like this, minus 2. It happens, w happens twice. Phi j transpose r minus j minus phi j wj. This is just a scalar function of wj, so it's very simple. I'll urge you to sort of just verify it yourself, and then lambda sine of wj. And let me try to simplify this. Let me change pen color so that 2 and that 2 cancel, and I get the coefficient of wj is phi j transpose phi j, and the minus sign goes away with this minus sign, so I guess phi sup j, I apologize, phi sup j transpose phi sup j times wj, and that's a 1 over n term, and then I have the negative term, which is phi j transpose rj, so minus again 1 over n phi j transpose r of minus j, I meant r of minus j, plus lambda sine wj. That's my entity. Let's interpret these terms. So this guy, let me change pen color again. This guy is just the jth feature, and this is normalizing over examples. This is a correlation of the jth feature against residual error from using all the other features, and again I'm normalizing by the number of examples, right? And then I have the sine term. So the derivative looks like this first term is just the energy of the jth feature normalized across examples, wj minus again the 1 over n, and I'm going to write this just as an inner product between phi j and the residual error when I use everybody else, plus lambda sine of wj. This is my del L by del wj. It's almost the same as what we had before, except it's just a little bit different. Let me just write down what this looks like. Remember when we had this other function which was half a minus w squared plus lambda magnitude w, that gave me the w minus a plus lambda sine w as my derivative, right? Now I have some positive number multiplying the w term, this positive number multiplying the w term. So my del L by del wj is some b wj minus a, but then again plus lambda sine of wj, where my this is my b term and this is my a term, right? That's what we have. And you can see immediately that if w is positive, then b wj minus a plus lambda is equal to 0. So wj is going to be equal to a minus lambda over b. If this is for wj positive, this is basically for a bigger than lambda, right? That's when you will get wj positive. Remember, b is positive already. B is bigger than or equal to 0 because b is this energy normalized by n, right? So remember, b is phi j squared divided by n, and a, I already said, is 1 over n, the inner product of the jth vector and the residual due to all the other guys, right? That's what we have. Similarly, if wj is negative, then I'll have wj minus a minus lambda equals 0, and so wj will be equal to a plus lambda over b, which is less than 0 only when a is less than minus lambda. And in the middle again you'll have that it's increasing for w positive and decreasing for w negative, the derivative, and so w equals 0 is the right solution. So the upshot of this is that I get wj is 1 over b times the shrinkage operator applied to a, right? And let me write that out again, remind you of what these things are. 1 over the normalization of the jth feature, and then s lambda of how the jth feature correlates against the residual error, again normalized across examples. So that's my solution to the minimization problem when I'm fixing everything except the jth coordinate of the regressor. So a couple of things to remember. Generally speaking, when I look at this term like this, phi w minus y squared, when I look at this, the reason I'm not having the bias term is because I've assumed that everything has been demeaned. Remember when we did the original problem, so we'll assume that these have been demeaned across examples, right? And then of course I have this term. The one thing I want you to remember is that if I also normalize the features, so if I, after demeaning, if I normalize the features, what does that mean? That basically if I look at the jth feature and sum up the squares over the example and normalize by the number of examples and set it equal to 1, that's basically normalizing the variance of the features. And that means I can, if I do that, and I don't necessarily always do that, if I do that, then I can get rid of the denominator term here. That's just going to be equal to 1. Anyway, so now we have basically, in this discussion, we basically talked about why it makes sense to do L1 norm regularization if you want sparse solutions, what the lasso problem is, and how one very nice way to solve the lasso problem is the cyclic minimization that basically says every time you basically, if the coefficient is not large enough, basically then you can set it to 0. That's what the shrinkage operation is doing. And one last note, while we have set up this lasso problem in the context of regression, it is actually applicable in the mathematical problem of basically doing a linear fit to some targets subject to some sparsity constraint is far more general, and we'll, for example, use it when we talk about compressive sensing as well. Now let's go back to the original problem, now that we know that the L1 regularization is a good idea, but let me go back to the original problem. What was it? It was that I want phi w to be close to the target, and I want w to be sparse. And then we set it up as quadratic plus L1 norm constraint, right? That's how we did it. Now there are other ways of doing it that basically try directly to go to an L0 sparse solution, but those are not guaranteed to have global optima. So one such approach is a greedy approach called matching pursuit, and you'll see the analogy and difference to this cyclic coordinate-wise minimization in a minute. So basically, what is this phi of W? It's basically the first column of phi times W1, second column of phi times W2, etc. I have D features, dth column of phi times WD. That is my phi W, and I want it to match Y, right? So we want to do a good want to match. So well, what if we just sort of say, okay, let me try to be greedy about, so I'm basically trying to match the column space to Y and trying to make the coefficient sparse. So how about choosing the smallest number of columns that explain the Y? Okay, so the greedy strategy would be to say, okay, I think of these phi j's, I normalize them in terms of unit directions, and so the projection of Y onto any of these guys is that number, and basically I'm going to say, let me check the max over this to explain the most amount of Y I can in any directions, right? So let's say the argument of the max of this is say j hat, right? So then I'll basically say, okay, I'm going to use j hat, and of course, what is the projection going to be when I do that? It's going to be Y onto the normalized version of j hat, the unit vector along phi j hat, times the unit vector along phi j hat. That's the projection of Y along that direction. And you can see that in terms of what's the if I want to write this as Wj times phi j, then the Wj is going to be Y projected along phi j hat divided by the let me just change paint colors to note that I've got these two norm terms. So basically I have it has to be divided by phi j squared, right? So that is my Wj hat. So it's a greedy strategy, and then I explain part of it, and then I'll then look at the residual, and that's going to be Y minus Wj hat. Let me correct the notation. Phi j hat, right? And now I'll apply the same procedure again among the remaining columns, which one is the best aligned. So I can, I guess, formalize this into an iterative scheme, and let me do that. So at the sort of the kth stage, suppose I have I sub k, which are say I1 through Ik. These are the chosen columns, and I have say some residual R sub k, which is basically Y minus W IL phi IL. So basically the guys I have chosen already. So my I sub, so this is L equals 1 through K, or I could also write it more generally as W I phi I in that set I sub k, right? So that's my current residual. And now if rk squared is less than some threshold, you can stop. So otherwise, I keep going. Otherwise, basically my I sub k plus 1 is arg max I not in my current set of the residual projected along the these guys, right? And then my w of I k plus 1 is of course going to be my residual, and then I k plus 1 here, and then it's norm squared there at the bottom, right? And that is called that is my greedy matching pursuit algorithm, and you can see that it'll go to a small number of bases. You think of the column, the features across examples as your potential basis functions, and you're trying to get to the smallest number of basis functions that you can. Now the different columns can have different levels of dependency, and so you could potentially if you've already explained part of the target, you may want to be less redundant and take into account the fact that there's some dependence across these columns, and that leads to an algorithm that is very popular called orthogonal matching pursuit. It means that you only look at the component that is sort of orthogonal to the current subspace. So let me just sort of define things clearly. So again, in recursive terms, so suppose you have I1 through Ik that has been selected. Again, there is this set of indices Ik, and let Sk be the subspace spanned by the corresponding columns, right? So subspace spanned by phi I1 through phi Ik, right? So it's a span of phi I such that I in Ik. Of course, you can maintain an orthonormal basis for this subspace by doing Gram-Schmidt on the columns that you have so far, etc. Let's not get into those details. Now, your best estimate of the target based on these guys is, under the linear model, is of the projection onto Sk of the target, and your residual at this stage is the target minus that, right? So it's the projection orthogonal to this subspace of the target. And now you just use a greedy procedure of pick phi I such that Rk phi over pi is the biggest, right? So arg max over I, not in the current set, not in Ik, and that is my Ik plus 1. So that's orthogonal matching pursuit. And again, when you add the new basis, new column, you might want to use Gram-Schmidt to maintain an orthonormal basis, and that's how you go along. And again, these things are all, there are packages for all of these guys, but I just wanted to sort of give you the key ideas behind them, which are sort of rather simple. So contrast this matching pursuit and orthogonal matching pursuit with what we were doing with this cyclic minimization strategy, right? For lasso, there too we were going, column by column, But we weren't being greedy. We're just going any arbitrary order would work, and we were applying a shrinkage operator and explaining the part that was not explained so far, and just going around. And there we were actually guaranteed to get to the global optimum. Here, there's no such guarantees, but these are greedy procedures that work really, really well. And often, if our objective is to get a sparse solution, meaning an L0 sparse solution, they might be better than the lasso in many scenarios, and they're often faster. So it's something to have under your belt. And the same comment that I made for lasso, that it is actually a very general purpose formulation, applies here too. Again, as I said, lasso can be thought of as sparse linear regression, but it can also be thought of that approach of sparse linear regression can also be applied to compressed sensing. And again, we'll get there when we get there.